Hello everyone, I am Vipin Kumar and we are back again on this GATE Ranker series. So yesterday we started with work and heat transfer and we are going to continue our same discussion today. Okay, I don't have audio. आपने audio. Hello, I hope my audio is okay now. So yesterday we started with work and heat transfer. We solved few questions, basic questions as well as advanced questions. Okay, we are going to continue today's discussion as well. So basically, first law of thermodynamics contains work and heat transfer, right? Especially for, a whole portion covers closed systems, but it comes into open system as well. Okay, so we are going to continue the same discussion. We are going to solve more questions on that, and we'll start our open system discussion as well, which we will continue tomorrow also. Okay, so today's discussion is again on first law of thermodynamics, where we will see work and heat transfer as well as the we will start our discussion on open systems as well. But let's continue today. So basically, before we start, a quick introduction. I have around 4+ years of teaching experience. I have done my MTech from Kharagpur. I have done also my MSc from Politecnico di Milano, Italy, and I was doing some research as well. I have some 1.5 years of industry experience, 2 years of research experience, and few international and national research publications as well. You will find me teaching or taking thermodynamics, heat and mass transfer, refrigeration, power plant, and all these subjects. Okay, let's move ahead quickly. So yesterday I gave you this question for just to try. I hope you have tried it. Good evening, Sachin. Good evening, Manav. Welcome to this session. I hope you were there yesterday. And I gave this question I gave you a brief idea also about this question. Okay, we draw the PV diagram and everything, and I gave you some idea about this. I hope you have solved this question. So could you please very quickly give me the answer so that we don't have to do this today? Yes. No, Bhavya, I don't think any data is missing. I don't think any data is missing. This is sufficient. Sufficient data is given. I told you, like, you have to convert into temperatures. Everything you have to convert into temperatures. So I hope, is anyone able to solve this question? Or should I go ahead and solve it for you? Quickly tell me if you want me to solve this question or you want to give another try. Because data is sufficient. Data is sufficient. Or should I move ahead for next questions? Okay, ठीक है, we will solve it. It's fine. We can solve it. Okay. So we discussed we have an ideal gas is heated at constant volume until we will go a little quick, right? Its temperature is 3 times the original temperature. Then it is expanded isothermally. Okay. So let's draw the PV diagram. Okay, we are heating, so pressure is going to increase, pressure and temperature. Okay, so this is your V1 is equals to V2, constant volume heating we are doing. Okay, so pressure is increased from P1 to P2. Then what are we doing? We are expanding isothermally. PV is equals to constant. And then it reaches original pressure. So 2 and 3 and we reach here. This is what is given. The gas is cooled at constant pressure until it's restored to its original state. Net work done we need to find out. Okay. So I hope you are all with me. They are giving that T2 is equals to 3 times of T1 and T1 is given as 350. So this is 350 into 3, which is I think 1050 Kelvin. right? This is 1050, right? 350 into 3. Yeah. So I know T2, I know T1 and T3, because 2 to 3 is what? Isothermal process, right? 2 to 3 is isothermal, so T3 is also known to me. T3 is equals to T2 is equals to 1050 Kelvin. T1 is equals to 350. Very quickly. Okay, so what do we have? Network we have to find out. W122 will be 0. Constant volume, I don't think we need to do something. Okay, constant volume process, W122 is equals to 0. W223 isothermal process. And how do you solve isothermal? What is the equation for work transfer? It is P2 P2V2 ln P2 by P3, or I can say P2V2 ln V3 by V2. Okay. Now, what do I know? I need to find out either pressures or volume. Okay. Are you getting this? Is this okay? This speed I think is fine, right? I'm not very fast. Okay. So first of all, P2V2 can I write MRT2? Yes, I can. ln V3 by V2. Now, what do I know? I know this is constant volume, right? Constant volume process. Constant volume, yes. Okay. So when it is constant volume, can I say PV is equals to MRT? M and R is constant, volume is constant. So P1 by T1 is equals to P by T is equals to constant, and I can say it is P2 by T2. Okay. So from here, can I get a relation that P1 by P2 is equals to T1 by T2? Yes, I can. P1 by P2 is equals to T1 by T2, right? Okay. So can I also say that P1 is equals to P3? Yes. So P1 is equals to P3, right? P1 is equals to P3 by P2 is equals to T1 by T2, right? You don't have R. R is for air, right? I mean, you can assume that. Okay, it's 0.287. You can take that. When ideal gas is given, okay, so you can assume it for air, 0.287. You can take 0.287 and solve it. Was that the only issue or anything else? No, air isn't given. Yes, air isn't given, but if the value is not given in the question, because I saw this was not given, okay, so you can assume that it works. Yeah, 287 joule per kg Kelvin you can take for air. Okay, so that was the thing. So now I know T1, I know T2, and P3 by P2 I need to put here. Okay, and I can write mRT2 ln, what is P2 by P3? P2 by P3 is T2 by T1. And you can put T1 and T2, you can find out. R you can take 1 kg, okay? R you can take 1. Oh, I'm sorry. Mass you can take 1. So what do you get by this? What do you get by this? Did you try this? Work 2-3 is 331.067. Yes, absolutely correct. 331.067 or okay, anyway, kilojoule per kg. Absolutely correct. Now, do I need to move ahead? Work 3-1. P V2 minus V1. P V2 minus V1, you can again turn into MR, right? MR T2 minus T1. MR T2 minus T1. Is this fine? What is the work for 2-3-1? What is the answer? Final minus initial. What is the answer? Very quickly tell me, we'll move ahead then. What is the answer? It's 200, right? 200.9. Is it positive or negative? Negative, yes. Because T1 is 350 and this is 1050. Okay, so it will be negative. Net work done. You can find out W12 plus W23 plus W31. Okay, what is the net? Work net is 130.167. Yes, correct. 0.167. Yeah, so let's move ahead, okay? No, it's not like this. Basically, R that you have taken, it is for air. Okay, maybe I'll check. Maybe if I'll review the notes that I have from which I have taken this question. So this question I have solved by using R is equals to 0.287. Let me check if this data is missing or not, and I can tell you tomorrow. Okay, I'll keep that in mind. It is not like that. You cannot do that. You cannot just take air. Okay. Now, very quickly we will move on to this question because I have a very important question that we need to solve. Okay. So very quickly we will move to this question. A piston cylinder arrangement as shown in the figure. Initially, what is the time? Yeah, very quickly we will move. A piston cylinder assembly arrangement as shown in the figure initially contains air. Look, here they have specifically given air and its initial pressure is 150 kilopascal. Initial temperature is 400 degrees Celsius. The arrangement is allowed to cool to the ambient temperature of 20 degrees Celsius. So we are cooling it. Q is coming out. We are cooling it. Okay. And heat is coming out and it is cooled down to final temperature T2 is equals to 20 degrees Celsius. We are cooling it to ambient temperature which is 20 degrees Celsius. Characteristics gas constant is given. The cylinder wall has stops of negligible thickness that can prevent the piston. So once the piston reaches here, it cannot go further down. Okay. That can prevent the piston from moving down. The stops are 1 meter from the inner side of the base surface. Okay. So this is 1 meter. and the piston is stopped at 1 meter above these stoppers in the initial condition, okay, in the initial condition. Now this is what we have given. Final pressure we need to find out. Final pressure we need to find out. Okay, some options are given. So let's try to solve this very quickly. What do we have? We have P1 is equals to 150 kilopascal. T1 is equals to 400 degrees Celsius. You converted that into Kelvin. How much is it? 6. It is 673, okay? Then what do you have? It is cooled down to a temperature T2, 20 degree, which is 293 Kelvin. Now, the process that is happening is cooling. Okay. Now the question is, what kind of cooling is happening? Is it constant pressure? Is it constant temperature? Is it constant volume? We don't know. So we cannot take anything as constant. 673 Kelvin. Yes, Sachin. Thank you. So we don't know what kind of cooling is happening. Okay, so I cannot relate. What I can do is I can make an assumption that air is behaving as ideal gas. That is an assumption. So it is going to follow PV is equals to mRT. It is going to follow this, okay? So when I am cooling, its pressure is also coming down, its temperature is also coming down, its volume is also decreasing, okay? Because I am cooling, right? So this is constant. PV upon T is equals to mR is equals to constant, and I can say that P1 V1 by T1 is equals to P2 V2 by T2. From here, what do I need to find out? I need to find out final pressure. P2 is equals to P1 V1 by T1 into T2 by V2. What do I know? I know this pressure, right? I know this temperature and I know this temperature. V1 and V2 I don't know. V1 and V2 I don't know. How do I calculate V1 and V2? How do I calculate V1 and V2? So you see, in the initial condition, piston is here. Piston is at this position 1. Now, can I calculate V1 is equals to area into height? Yes. So V1 is equals to area, this area, okay? This area. Whatever the circular area here is, that area. So area into height is 2 meters. So this is 2a meter cube. Right? Next, V2, yes, absolutely correct. V2 is equals to, it will stop here. So V2 is equals to area into height. What is height? 1. So 1a meter cube. That is what I am going to substitute here. And could you please quickly tell me what is the value of P2? Very quickly you put all the values. P1 I know, V1 I know now, it is 2a. T2 also I know, 293. How much is P2? How much is P2? Have you calculated it? P2 is equals to, should I calculate it? 130.61, absolutely correct. Yes, absolutely correct. Okay. Now let's move on to one of the important questions that I wanted to solve today. Okay, this question. So what is happening here? Let's see. We will try to understand it point by point. Okay. Argon at 39.85 degrees Celsius with a volume of 0.5 meter cube is initially contained in a piston cylinder arrangement whose cross-sectional area, so piston cross-sectional area is, this cross-sectional area is 0.7 meter square, and total height, this total height is 5.7 meter. Total height is 5.7 meter. And it is contained like this, and here the initial pressure and initial temperature and volume is given. T1 is given and volume 1 is given. Okay, 0.5 meter cube. Now it consists of a massless piston loaded with water at 20 degrees Celsius. This water is at 20 degrees Celsius, and outside atmosphere, as shown in the figure, if the piston just touches, if the piston comes here and touches this stop, then the whole volume is 0.8 meter cube. Now we are adding heat until the temperature of argon reaches 251. So final temperature is 251.85. Plot the entire process on PV diagram. Assume piston to be adiabatic. Okay. So let's move. Sachin, yes, that is correct. That was correct for the last question. Let's focus in this on this question. This is very, very important. Okay. We'll see a lot of things here. Okay. So this is what it is happening here. Now what do I know? I know, look, P1 is not given. T1 is 39. Tell me how much is it in Kelvin? How much is it in Kelvin? T1, V1 is given 0.5 meter cube, and T final they are giving us, T final is there 20 degrees Celsius. No, T final is 251.85 degree Celsius. So how much is it? 39.85. It is 312.85 Kelvin. And how much is this? Plus 273, 524. Okay, now what am I doing? I am giving it heat. I am giving it heat, okay? So when I am giving heat, the piston is moving up. The piston is moving up. But piston will stop here. Piston will stop here. Now I don't know if I am still adding heat or I stopped. So I don't know if this final temperature is the temperature when the piston reached here, or I am still giving it heat. So I am not sure. So what I have to do? I have to draw a PV diagram. PV diagram. PV diagram I have to draw. So when the piston will go up, I am sure of one thing. What is that thing? That piston is going up means volume is increasing and pressure is decreasing. Okay. So what is happening? I am here and slowly, how the piston is moving up? slowly it is going up and the water is falling. Okay, it is very slowly it is going up. So it's a linear relationship between pressure and volume. It is a linear relationship. P1 is here, P2 is here. P1 is here, P2 is here, V1 is here and V2 is here. Okay, this is my PV diagram. Now I need to find out the final pressure. The final pressure I need to find out. Okay, so first of all, what I need to do, I need to find out P1. How will I find P1? So you see, here it's P1, but what is the pressure? What is the pressure here? Pressure will be atmospheric pressure plus this water pressure, whatever water is here. Okay, so can I say P atmospheric plus water? It is rho GH. Okay, now atmospheric pressure they have given us. Atmospheric pressure they have given us 101.203 kilopascal. It is 101.203 kilopascal plus rho GH. How do I calculate this? So I can write GH by specific volume. Okay, now I need to find out H. How do I find out H? P1 is 143.23. No, that is not correct, I think. It's given adiabatic. So why we are considering? No. They are saying piston is adiabatic. Piston is not. Piston cannot transfer heat. There is no heat transfer that is going to happen from piston. Piston is adiabatic. Heat transfer process is not adiabatic. Hello Subdeep. Hi Pandav. Good. Naam. Okay. So Bhavya, I hope we are clear. You see, what they're saying is that, where is that? Nowhere it's written. Where is adiabatic? I can't see adiabatic. It's given adiabatic. So why? Where is adiabatic? Okay, no, adiabatic is not there. But even if the question tells you that the piston is adiabatic, means there is no heat transfer through the piston. Yeah, where is it written? Piston is adiabatic. With a volume massless piston loaded with outside atmosphere. Okay, anyway, yeah. But as I am telling you, if they are saying piston is adiabatic, it does not mean that the heat transfer is adiabatic. It simply means that through the piston, no heat transfer will happen. Okay. Here and here, no heat loss will happen. It simply means that if they are saying piston is adiabatic. Okay. This heat transfer is not adiabatic. Okay. Okay. So specific volume. Now I need to find out this H. What is this H? So this H is, if this is piston here and the whole height is 5.7, then I need to find out this height. How do I find out this height? V1 is given. Okay. So V1 is equals to area into height. V1 is given as 0.5 and area is given as 0.0.5. Area is given as 0.7 meter square. Okay, so it is 0.7 into h. So what is this H? 0.5 by 0.7. How much is this H? Yes, that is correct, Bhavya. It is 150 kilopascal. Okay. So you can find out H here. How much is H? H is 0.714. And now I have to, this is H dash, okay. Now H is equals to 5.7 minus H dash is equals to, how much is it? It is 4.9, okay, meters. You put it here, you know, it is 101.203 plus 9.807 into height is also, we have find out 4.9, and specific volume is also given. This is the specific volume of water, specific volume of argon. Okay. Okay, so it is 0.00102. Okay. (1002). And that is 150. Of course, that is 150 kilopascal. Okay. Now I need to find out when the piston reaches near the stoppers. When the piston reaches here, what is the pressure? Can you find out very quickly what is the pressure? P2 is equals to P atmosphere plus rho GH double dash, let's say. This is my H double dash. How do I find out this? How do I find out H double dash? Now they have given when the piston touches the stoppers, the volume V2. Volume V2 is 0.8 meter cube. So V2 is equals to area into H. H triple dash, and I can find out H triple dash is equals to V2, which is 0.8 upon 0.7. How much is it? How much is it? It is 1. H double dash is 4.1. That is correct. H double dash is 4. No, it is not 4.1. You just check it correctly. Well, how much is this? H triple dash. It is 1.143. So H double dash will be 5.7 minus 1.143 meter. Now how much is it? Yeah, now how much is this? (5.7 minus 1.143). Yes, 4.557 meter. So I need to substitute it here and I can calculate P2. Can you tell me how much is P2? Can someone tell me how much is P2 very quickly? P2 is 145.804. 145.804 kilopascal. Now, there is a point here, okay? What I am doing, my piston was here and I am giving heat, okay? And I am giving heat. So when I am giving heat, my piston is moving up. Now, as soon as the piston reaches at the stops, the pressure is 145, okay? As soon as I reaches the stops, the pressure is 145. Now I need to find out what is the temperature there, because I need to find out, did I stop the heating as I reached the stops or did I not? Am I still supplying heat? How would I find that out? So what will I do? You see, heat transfer is happening. But I don't know what is the process, okay? I don't know what is the process. So simply what I am going to do, P1 V1 upon T1 is equals to P2 V2 upon T2. Everything I know. P1 I have calculated, P2 I have calculated, V1 is 0.5, V2 is 0.8, okay? And T1 is also given to me. T1 is also given to me is, how much is T2, T1? 312. Can you find out what is T2? Very quickly, could you please tell me how much is T2? Can someone very quickly tell me how much is T2? How much is T2? Are you guys calculating? T2 is 486.557, absolutely correct. 486.557 Kelvin. But in question he is saying that the T final is how much? T final is 524 Kelvin. They are saying that it is 524.85 Kelvin. Now you see what is happening. Let me tell you what is happening, okay? You see, piston is here. You are giving heat, okay? You are giving heat. So its pressure is changing, its temperature is changing, okay? Its pressure is changing, its temperature is changing, and its volume is also changing. Now, when the piston reaches at the stop, its pressure has decreased, okay? Its temperature has increased, okay? But we have not stopped. He is saying its final pressure is this, its final temperature is this. So that means when the piston reaches here, the temperature is this. When the piston reaches at the stops, okay? So when piston is here, you are giving heat. As soon as piston reaches at the stops, temperature is this. But he is saying that the final temperature is this. That means that we are still giving heat. So we are still giving heat, but the volume is constant. Volume is stopped at the stoppers. Pressure and temperature can change. Pressure and temperature can change, but volume is fixed because there are stoppers. Piston cannot go up. Okay? Piston cannot go up. So we are still giving heat. We have not stopped. So basically this diagram is still not completed. It is when you have reached at the stops. Now the volume is constant and you are still giving heat. You are still giving heat, okay? So we have to find out what is the final pressure when temperature is this. What is the final pressure when temperature is this? How do you do that? Very simple. Instead of this, you can put P final, V final upon T final. You can use this, okay? P final I need to calculate. What is V final? What is V final? Yes, pressure will change. Pressure will change, of course, because now volume is constant, pressure and temperature will change. Okay. Earlier, when the piston was moving, pressure was decreasing because volume is increasing. But now volume is constant. So as you know, right, when volume is constant, pressure is proportional to temperature. So if temperature will increase, you are giving heat, temperature is going to increase, pressure is also going to increase. Okay. So what is happening here? What is happening here? You know P, you have to find out PF. What is VF here? VF is equal to V2 because volume is not changing. Once we have come at the stop, volume is not changing, volume is constant. Okay. So V final is equals to V2. T final they have given in question. You have to find out final pressure. Final pressure is 157. Let me check. Yes, that is absolutely correct. Final pressure is, from here you can find out, final pressure is 157.28. So now you see what is the final pressure. So what is going to happen? You have come here. Here pressure is decreasing, volume is increasing. Now once I have reached here, I have reached this point. I have reached at point 2. But now volume is constant, I am still giving heat. So my pressure is increasing at constant volume. So my pressure is increasing and my pressure will go somewhere here, which is how much? So this one, P is equals to, P1 is equals to 150. P1 is equals to 150, and finally you have reached somewhere here, which is 157. So basically this is its PV diagram. Is this okay? This is its PV diagram. I hope you are able to understand this. So basically when I have reached at this point, I did not stop, I am giving its heat. So it's now constant volume heat addition. Now I know. Earlier I did not know what kind of heat transfer is happening. But now I know that constant volume heat transfer is happening. So pressure is going to change and temperature is going to change. This much is clear or not? This is clear? So we will move ahead. So P final they were asking, we have calculated P final. Okay. Now they are asking calculate the work done in kilojoule. Okay. P1 is equals to 150 kilopascal. P2 is equals to how much? 145, right? 145.8, and P3 is equals to 157 point, I don't know. Now can someone, yes, I can tell you, of course. Look what is happening. Okay, look, this is my piston, right? Now my piston is there, and over piston I have water. Now my piston is not moving freely. What is happening? Very slowly I am giving heat. Very slowly I am giving heat, and very slowly the piston is moving as the water is spilling outside. Okay, the motion of piston is it's a quasi-static process. Okay, so one by one you are moving step by step. Okay, so very slowly your pressure and volume is increasing. Okay, so it's not an exponential relation. For example, in spring forces, what you do, you take a linear relationships. Okay, so very slowly when you are moving, because if this water is not there, then I don't know what kind of relation is there. For example, instead of water, if you put some weights on it, okay, if you and you very slowly remove one weight and you let the piston move up. So if that kind of motion is happening, that means its pressure and volume is very slowly increasing. Okay, it's very slowly changing. And then we assume that it is a linear relationship. Okay, if this water is not here, then I don't know, it could be exponential, it could be any relationship. Okay, it could be rectangular hyperbola, how, I don't know. But this I know, if I have weights above the piston and you are very slowly removing weight, then the relationship is linear. Okay, I hope that is clear. Okay, I need to find out the work done. Can anyone tell me how to find out the work done? Work done is equals to, this is 1, this is 2, and this is final point. Work done is equals to work done in this 1 to 2 plus work done from 2 to final. Okay. So can you tell me how to find out W12? W12? W is 44.37. Yes, absolutely correct. Okay, I think that is correct. Yeah. So you see, look, you have this, you have a, now you have to find out this area. You have to find out this area. Okay, you have to find out not this area, this area. How can you do this? You can find out this rectangular area and then minus this triangular area. Okay, so you know how to calculate the rectangular area. We all know, okay, height into width. Okay, and we know V1, we know V2, and we also know how to calculate triangular area. We can cut that. Okay, so if you solve that, you can do, and we already know how, what we can do, half P1 plus P2 and V2 minus V1. Okay, this is what we can do. It's the same thing. If you do the derivation, you will find out. Okay, so this is this work 2F is 0. It is constant volume work. It is constant volume work. So when you do that, Bhavya has calculated it is 44.37 kilojoule. That is absolutely correct. Okay, so that is absolutely correct. And now we'll move to the final part of it, heat transfer during this process. Heat transfer. So Q1 to final is equals to Q1 to 2 plus Q final. Okay, Q final. So can you do that? Now I can also say that dq is equals to du plus dw, because I have already calculated dw. And can I say it is m cv t final minus t initial plus dw 44.37. How much is it? Can you tell me what is the, achha, in question cv is given. In question cv is given. How much is it? This is cv 0.312. This is cv. You can put this and calculate that. Is there anything that is required? What is required? I know. Can you calculate mass? Are you able to calculate mass? You can do P1 V1 is equals to mRT1. Mass you can calculate by P1 V1 upon RT1. We know everything. We know everything. Okay? Are you able to calculate this, or should I do it? R is also given to us 0.2081. Okay? R is also given to us. This is R. You can write down the values of R and CV. I did not change the notation because it was given like this in question. It's a ESC question 2022. So I did not change the notation because it was given like this. Are you solving this? Is anyone solving this to calculate heat transfer? Yes, it's 120.56. Is anyone else solving this? Yeah, it is absolutely correct. 120.57 kilojoule. Okay, 120.57 kilojoule. Okay. Now very quickly let's move on to this question. Okay. Now what is happening here? Air is held inside a non-insulated cylinder using a piston of mass 25 kgs and area 100 centimeters square with stoppers. The initial pressure and temperature of air inside the cylinder are 200 kilopascal and 400 degrees Celsius. Ambient pressure and temperature are 100 kilopascal and 27 respectively. The temperature of the air inside the cylinder at which it will begin to move is. Let me give you some idea what you have to do, and you try this on your own, okay? And we will discuss that tomorrow. Now you see, when this piston is wherever it is, there is some atmospheric pressure, it is working on it, and weight, body weight, okay? And here it is air pressure. It's air, right? Yeah. Now this is given as 200 kilopascal. 200 kilopascal. Okay, 200 kilopascal. And this is P external is equals to P atmospheric plus because of the weight. Okay. So P1 is equals to, what is 200? No. So basically what you have to see here, that P atmospheric is given to us, atmospheric pressure is 100 kilopascal. And what is this? Force per unit area, mg by area of piston. Okay, by area of piston. Now mass is given, area is given. You can find out what is the external pressure. How much is the external pressure? How much is the external pressure? Mass is 25. So this is 25 kg into 9.81 meter per second square, and area is 0.01 meter square. And you have to take care of the units. You have to, no, it's not 75. Okay, try to solve this. You have to take care of units. It is in kilopascal. What is this? This will be in pascal. Okay, Just try to check this, try to check one more time. Are you able to solve this very quickly because our time is almost over? (25 by into 9.81 divided by 0.01, and you have to divide everything by 1000. Yes, P external is 124.525. That is correct. 124.525. Okay. Now they are saying you have to find out the temperature at which the piston will start moving. Now when the piston will start moving, piston will move down. Piston will move down only when pressure of air is less than or equal to, I mean less than or equal to P external. Okay, basically it's less than. So what is the minimum value of P air? P final should be 124.5 kilopascal. That is the final pressure. That is the final pressure. Okay. So now you can apply a ideal gas equation here. Now you can apply a ideal gas equation to find out what is the temperature. Okay. Try that. P final I have gotten, P initial I had already, okay. P1 V1 by T1 is equals to P2 V2, or P final I can say by T final. Can you find out T final? Can you find out T final? T final is equals to 419 point. Yeah, that's absolutely correct. Okay. I hope you were able to figure out that V1 and V final will be same. Okay. So T final is 41. Sachin, that is correct. Little bit, maybe you are mistaking with some values, but that is correct. It is around 420 Kelvin. Okay, it is around 420 Kelvin. So both the answers are correct. There could be some round off issue that you will be facing. Okay. Okay. So let's. What is the time? Okay. Okay. This question you write down. You have to try this question. Very easy question. Okay. And you have to give me answer tomorrow. Consider the following internal energy. U1 is given, U2 is given, and U3 is given. And you have to find out heat transfer during this process 1 to 2 and check if this statement is correct. Heat transfer during process 2 to 3, you have to check if it is correct or not. And work transfer and total work done. You can take a screenshot of it and you can try this. I will take the answers tomorrow. Maybe take a screenshot of it and we will. And very quickly we will come to the last question. I hope you have taken the screenshot. Could you please confirm if you have taken the screenshot? Sachin, take maybe note down or take a screenshot of this and we'll move ahead. Okay, so we are moving ahead, right? Okay, last question for today. Last question. Air enters. Now we have started open system, okay, and we will continue tomorrow open and closed system. I'm sorry, open system, steady and unsteady flows. Okay. Now air enters an adiabatic nozzle. We have a nozzle. And air is coming in. It is adiabatic, okay? So no heat transfer. Air is coming in at P1. Here P1 is equals to 300 kilopascal. T1 is equals to 500 Kelvin and V1 is equals to 10 meter per second. And then it leaves the nozzle at P2. I hope you are able to see what I am writing. 100 kilopascal and V2 velocity 2 is equals to 180 meter per second. Specific heat and inlet area is also given. The exit temperature of the air is, exit temperature you have to find out. So we all know nozzle is a steady flow device. Okay, nozzle is a steady flow device. So can I apply steady flow energy equation here? Steady flow energy equation. What is that? What is that? H1 plus V1 square by 2 plus GZ1 plus if any heat is coming in is equal to H2 plus V2 square by 2 plus GZ plus if any work output is happening. Is this right? Is this right? Are you able to follow this? Now, we all know that it's a adiabatic nozzle. It's a adiabatic nozzle, no heat transfer, no heat transfer. So this is 0. Is there any work output? No. In nozzle, there is only a fluid flow. There is no work output. Okay. So this is also 0. And I have to assume that there is no potential difference as well. Okay. This height is same. The difference is not. The difference is not significant, okay? So I can neglect this as well. Now very quickly tell me what is, can I write H1 plus V1 square by 2 minus V2 square by 2 is equals to H2? Yes, I can. Okay. Now, can I write CPT1 plus V1 square minus V2 square by 2 is equals to CPT2? Yes, I can. Right? So, can you calculate T2 from here? Can you calculate? Can you tell me very quickly what is C2? So, I can write T2 is equals to T1 plus V1 square minus V2 square upon 2 Cp. 2 Cp. Can you calculate T2? T2 is 483.9. T2 is 483.9. Absolutely correct, Bhavya. Very nice. 483.9 Kelvin. Okay. 483.9 Kelvin. So 484. Okay. And they are asking the exit area of nozzle. Exit area of nozzle. So is there any doubt in this exit area of nozzle? Okay, it is a steady flow device. Okay, so we can apply continuity equation. What is continuity equation? Mass conservation equation. Okay, mass that is coming in, mass in is equals to mass that is going out. There is no accumulation. Okay, in the nozzle there is no accumulation. Whatever is entering, it will go out. There is no accumulation of mass. Okay, so can I write rho 1 A1 V1 is equals to rho 2 A2 V2? I can write. So what you need to calculate? Exit area. So A1 V1 upon specific volume 1 is equals to A2 V2 upon specific volume 2. Now we also know it is air. So can I write? Can you calculate it very quickly? How much is it? PV is equals to MRT. P specific volume is equals to RT. Specific volume is equals to RT by P. RT by P. It is no, it's not 4.44. I am sorry, I don't think it's 4.44. Just check it again one more time. Okay. So can I write A1 V1 upon R T1 by P1 and A2 V2 upon R T2 by P2? R and R will get cancelled, and now I think I have everything to calculate. Okay, just check. I am not sure about the answer. Just check if your calculation is correct. Okay, so can I write area 2 is equals to area 1 velocity 1 by T1 into P1 velocity 2 into P2. Just check what you are getting. 12.9, that is correct. So what was the mistake earlier? 12.9. That is correct. Sachin, are you able to solve this? I mean, are you able to understand this? Is this okay? Okay, you cancel the density. Okay, so that is 12.9. 12.9 what? Centimeter square. ठीक है? Okay, okay. Sachin, you can like if there are some doubts, you can ask. Okay. 12.9 centimeters square. Very nice. Very absolutely correct. Okay. So now I hope you have noted down this question. We will talk about this tomorrow. You give me tomorrow which options are correct. Okay. And if there is any doubt, we can discuss this tomorrow. Is this all right for today? So we will wrap this up. Just try to solve this and give me the options which one are correct. Okay, so we will wrap this up here. Thank you very much. Thank you. And we will meet tomorrow. We will take open system questions. Okay, steady flow and unsteady flow. So a lot of people get confused in unsteady flow questions, and we will see how to simplify them. Okay, so we'll see take that tomorrow 6 p.m. at the same time, and I am going to see you there. Thank you very much.
आवाज आई नहीं।
हाँ पहले खराब है,
हाँ ये खराब
खत्म कर दिया।